What if I told you that beneath Antarctica's frozen wasteland, there's a hidden water world that could completely reshape our understanding of climate change? And here's the part that will blow your mind. Scientists just discovered 85 brand new lakes lurking miles beneath the ice, and they're actively changing the fate of our planet's sea levels. Beneath Earth's most massive ice sheet lies a secret network of hundreds of subglacial lakes that most people never knew existed. These aren't just puddles under ice. They're dynamic, living systems that fill and drain in mysterious cycles, directly influencing how glaciers move and ultimately determining how fast our oceans will rise. Using 10 years of cutting-edge satellite data from the European Space Agency's CryoSat mission, researchers have just uncovered 85 previously hidden lakes buried several kilometers beneath Antarctica's frozen surface. This groundbreaking discovery doesn't just add to our lake count, it increases the total number of known active subglacial lakes by more than half, bringing the grand total to 231. But here's where it gets controversial. These findings, published in Nature Communications, suggest that our current climate models might be missing a crucial piece of the puzzle. The research reveals new underwater drainage networks, including 5 interconnected lake systems that operate like hidden rivers beneath the ice. Sally Wilson, the doctoral researcher from the University of Leeds who spearheaded this investigation, puts it bluntly. Our knowledge about these subglacial lakes and their water flow patterns has been severely limited because they're entombed under hundreds of meters of solid ice. Observing these subglacial lake filling and draining events under such extreme conditions presents incredible challenges, particularly since these cycles can take months or even years to complete. Wilson explains. Before our research, scientists worldwide had documented only 36 complete cycles from initial filling to final drainage. Our study contributed 12 additional complete fill-drain events, pushing the global total to 48. This is exactly where satellite technology becomes a game-changer in scientific discovery. The CryoSat mission, launched in 2010 as part of ESA's Future EO program, created an unprecedented dataset spanning an entire decade from 2010 to 2020. Picture this. CryoSat functions like a highly sophisticated ice detective, using its radar altimeter to measure polar sea ice thickness and monitor height changes across ice sheets covering Greenland, Antarctica, and glaciers worldwide. This instrument can detect incredibly subtle variations. We're talking about tiny changes in ice surface height that reveal what's happening far below. The research team used this decade-long treasure trove of CryoSat observations to identify localized height changes across Antarctica's icy surface. Think of it like watching the ice breathe. It rises and falls as underground lakes fill and drain at the ice sheet's base. This allowed scientists to not only detect and map these hidden lakes, but also monitor their cyclical behavior over extended periods. Anna Hogg, study co-author and professor at the University of Leeds, shares a fascinating revelation. We discovered that subglacial lake areas actually change size during different filling or draining phases. This demonstrates that Antarctic subglacial hydrology operates far more dynamically than anyone previously imagined, making continuous monitoring of these evolving lakes absolutely essential. And this is the part most people miss. These observations aren't just academically interesting, they're vital for understanding how ice sheets function structurally and their impact on surrounding oceans. Wilson emphasizes a critical gap. Current numerical models used to project how entire ice sheets contribute to sea level rise completely exclude subglacial hydrology. These new datasets documenting subglacial lake locations, boundaries, and temporal changes will revolutionize our understanding of water flow processes beneath Antarctica. Martin Waring, ESA's Polar Science Cluster Coordinator, reinforces the mission's significance. This research once again proves how crucial CryoSat mission data is for advancing our polar region knowledge, especially regarding ice sheet dynamics. The deeper our understanding becomes of complex processes affecting the Antarctic ice sheet, including meltwater flow at the ice sheet's base, the more precisely we can project future sea level rise scenarios. But how exactly do these mysterious subglacial lakes actually form? The process is more fascinating than you might expect. Subglacial meltwater originates from two primary heat sources. Geothermal energy radiating from Earth's bedrock surface and frictional heat generated as massive ice masses slide across underlying bedrock. This meltwater accumulates on the bedrock surface, creating pools that periodically drain through natural channels. Here's the concerning part. This flowing water potentially reduces friction between ice and the bedrock foundation it rests upon, essentially acting like a lubricant that allows ice to slide more rapidly toward the ocean. Imagine ice sheets as massive conveyor belts and subglacial water as the oil that makes them move faster. Not every subglacial lake exhibits active behavior. Many remain stable because they show no known filling or draining patterns. The largest documented subglacial lake, Lake Vostok, lies beneath the East Antarctic ice sheet, containing an estimated 5,000 to 65,000 cubic kilometers of water beneath 4 kilometers of ice. To put this in perspective, Lake Vostok holds enough water to completely fill the Grand Canyon and still overflow by at least 25%. While Lake Vostok appears stable currently, consider this unsettling scenario. If it ever drained, the consequences would dramatically impact Antarctic ice sheet stability, surrounding ocean circulation patterns, marine ecosystem habitats, and global sea levels. The implications for climate modeling are staggering and potentially controversial. The cyclical filling and draining patterns of subglacial lakes provide crucial data for ice sheet and climate models. By monitoring these phenomena, scientists can significantly improve their understanding of complex interactions between ice sheets, bedrock, oceans, and atmosphere. Knowledge that's absolutely essential for predicting ice sheet stability. Subglacial hydrology represents a missing component in numerous ice sheet models, Wilson states emphatically. By mapping precisely where and when these lakes become active, we can begin quantifying their impact on ice dynamics and substantially improve projections of future sea level rise. But here's the million-dollar question that should spark debate. If these subglacial systems are so dynamic and influential, how many other critical processes are we potentially overlooking in our climate predictions? Are we underestimating the speed at which sea levels might rise because we've been missing these underground influences? What do you think? Are we discovering these hidden systems just in time to adjust our climate models, or have we already missed crucial windows for accurate prediction? Should this discovery make us more optimistic about our scientific capabilities, or more concerned about what else we might not know? Share your thoughts on whether this groundbreaking research gives you hope or heightens your climate concerns.